I would like to thank the organizers for inviting me to give a second talk in this meeting. So last week I talked in the mathematical physics division of the meeting. So it's and certainly there was some integrability to what I said. So today I think this talk is going to be a little marginal to the main theme of this meeting, which is integrable systems. Although you'll see that I'll use integrability in my slides. You'll see in a moment. But actually, certainly there's going to be some statistical physics, and I think this will still appeal to most of the people here in this audience. So because this also relates to gauge theory, so it's a problem in gauge theory that I'm trying to solve, and gauge theory has been a framework that has been very, very important in condensed matter physics, and I think even it's becoming even more important. So, but as I said, a little marginal to the main topic of the meeting. Okay, so let me maybe state some mantras of statistical physics. So I think this is most people will agree that statistical mechanics is a subject driven by examples. For example, these integrable systems that this meeting is focusing on. And quite often, these models are built just from very minimal tools. So it's it's easy to explain what is actually your model, and then you want to solve it somehow. You want to study and have enough information to say something interesting about it. And then there are statistical mechanics is a fascinating subject because it works in this way. So usually the models are are defined as models of, for example, particles interacting or fields interacting. And then you have this thing called the thermodynamical limit, where there's some simplification, and then there's some global features that you actually observe. So, of course, these particles there's lots of information governing the dynamics, but then, from afar, you'll see that the system will have some features that you can describe using thermodynamics. And perhaps even more fascinating is to go the other way around, because sometimes you can have some, so you can put your hands in this thermodynamical behavior of the system, and for example, using some viral expansions or something like that, you can infer information about the interactions of the particles. Okay, so in my talk today, I think I can promise you that yes, it's an example. It's not really, it does not have to deal with integrability very directly, but it's an example in statistical mechanics where there are some interactions which are very interesting, and you can solve completely. So you can compute the partition functions as I will show you, in closed form, and you can derive, equation of state and all of that, So exactly. And then I think this is maybe even a more attractive feature that, yes, it is built from just very little information. I'm going to tell you in a moment the ingredients that I need to specify my model. And this can also be generalized using just, the same sort of simple framework. And yes, and then there is this thing that I'm advertising. I can actually compute partition functions and I can deduce thermodynamics. And you're going to see these at the end of the talk. What I don't have at the moment, I cannot promise you, is that I can actually use these sort of explicit quantities to say something about the interactions. I cannot quite do at the moment, but I think it would be quite interesting. So, and I think this is maybe not even beyond what, professional statistical physicists, which I think I'm not really, can maybe say, better than me. So I would like to have some, help from people in the audience that have some ideas. So how can I get from my equation of state, say something about the interactions that I'm going to, introduce you to. So it's a very interesting example because, so here the interactions are not built in from a potential, they are actually built in geometrically. So it's, so the interactions in the sense of there is a space of multi-particles, okay, that has a metric, which some curvature, and this metric contains information about how these particles interact. I'm going to explain all of these. Okay, so this is the outline. I'm going to start by introduce you to gauge sigma models. So this is a setting which I think should be appealing to condensed matter physicists, because people in condensed matter have used sigma models, so maps, for example, from a surface to some target, okay? And this is something that is coming in some of the talks this week. And then people are also interested in models that involve gauge fields, but usually just with linear targets. So you say you specify a representation of your structure group, and then you have you introduce matter coupled to the gauge field, but this is usually just a representation. It's just a linear target. So here I'm mixing both. I'm interpolating between the sigma model, as you know it, non-linear, with a target which has interesting topology and geometry, and the gauge theory. So it's something that interpolates between the two. And I'm actually going to focus for most of my talk in the simplest example, which is a case where you have a surface. This is where your field theory is defined, okay? And then you have a target, which is a two-sphere. It's the simplest possible compact target, which has very nice, very simple geometry, and I'm equipping the two-sphere with a round metric, and then there is this symmetry of rotating around an axis. Okay? Which is what I'm going to gauge. I'm going to gauge this symmetry. And now my meta field is not going to be a map to P1. It's going to be just locally a map to P1. So it's going to be a section of a bundle, so a fiber bundle where the fibers are two spheres. So this is how you should think about it. Okay, so locally it's a map to P1 from a bit of the surface, but globally it does not have to fit into a global map from the surface to P1, okay? So this is the general idea. And then you're going to see that there's some equations called the Vortex equations that describe the minima of the potential. So there's going to be some kind of a vacuum which is going to be degenerate, and then there's still some interesting geometry and dynamics that is induced by this geometry. Okay, so this set of minimal configurations is described by these vortex equations that I'm going to describe in a moment, and then this is how I think about this. So there's going to be geometry, so a metric on this space of vortex solutions. I'm going to look at the space of solutions modulo gauge symmetry, okay, and this is going to be a very nice space, and I'm going to try to say something about the metric there. And in this case of, so vortices with toric targets means that, so this is the simplest example of a toric manifold, but we can sort of generalize this greatly. And then, so as I said, the metrics, they encode interactions, and it's especially interesting to understand them in some asymptotics that I'm going to explain. So I'm going to explain you what it really means by asymptotic geometry. And then the statistical mechanics. So I think everyone here possibly almost everyone is interested in statistical mechanics. So you have to wait until the end of the talk for me to tell you about particular functions and so on. Okay? So you have to bear with me. Okay? So I have to say, to be honest, that the content of this talk is actually a byproduct of a much larger project, which involves several people. So some people that do topology. So Marcel Buxted, Christian Wegener, they are topologists. So it has to do with characterizing some ground states in some supersymmetric quantum field theories, where these vortex equations play a role, and these metrics and so on. So we are interested in just understanding these ground states non-perturbatively, and then we have to count what is called L2 Betty numbers of these metrics on the modular spaces. And this involves many different sort of sub-projects. So there are some papers in the archive that you can consult, and there's more papers that are still not in the archive, and but I hope there will be soon more. There will be more in the archive for you to read. So anyway, so these people are topologists. These people are more analysts, Martin Spate and Akos Neitsch. And my talk today is going to be based. It's going to be based on this, especially on this paper that we've put in the archive about a month ago, Martin Spate and I. Okay, so almost everything that I'm going to say is going to be contained here, so you can just, read there. So I'm going to skip lots of details, lots of calculations. Okay, so the first part is to tell you what are these gauge-figure models and what is the role of the vortex equations more precisely, okay? So these are the ingredients. So I advertised that I'm going to start with the minimalistic toolkit, so I think this is true. So I'm going to start with this surface sigma, which, it's just this. So a Kähler structure on an oriented surface. So it just means that, I have, if you like, an oriented surface with the metric, with the Riemannian metric. Just that. So a metric will induce a complex structure and also a symplectic structure, which is the area form. But this is basically how I think of it. And then there's going to be another Kähler manifold, which is a target. So you have to specify another Kähler manifold. So here, for example, P1 with the Fubini study, structure. Okay. And now there is going to be symmetry. So the target will be, acted by some compact Lie group. So in this case, it's just a circle. Okay. And then this action has to be, holomorphic, so by holomorphic vector fields. So again, the target is Kähler. So it's both a symplectic manifold and a complex manifold in a compatible way. And the action is also going to be Hamiltonian. So there's going to be a moment map. Okay, so a moment map. And so a moment map, I'm going to think of these moment maps as actually valid not on the dual Lie algebra, but on the Lie algebra itself. It's convenient to do that. So here I'm using the sort of musical isomorphism that is induced by an inner product on the Lie algebra. So actually, so you can think of this as you are going to equip the Lie group itself with a metric, which is invariant. Okay. So any questions? This is just very. So I hope everyone agrees so far that I'm using a minimal toolkit, and I'm actually going to restrict to the simplest example, which is the target P1, compact and not linear. So it's the case where it's beyond linear, and compact makes also things. So this is really the easiest example of an action like with these properties. Okay. So now there are some fields. So I'm going to think of these generally in this term. So I'm starting with the principal G bundle on the surface, okay, and then A. So the gauge field is just a connection on this principal bundle, okay, and the matter field is a section of the associated bundle that you get by using having this principal bundle and then using the action of the group on the target. So this is something that people do all the time for vector bundles, but it also works more generally for so fibers that are also not just vector spaces. Okay, and now there's going to be in this problem a topological charge. So the topological charge is going to be a class in the equivariant to homology of the target. Okay, so. So I think you might be, you have, for example, familiarity with the Abelian-Higgs model, let's say, which is basically exactly that. But now the target is just C. For the Abelian-Higgs model is just C. We are generalizing the Abelian-Higgs model to be have a nonlinear target. This is really the simplest generalization. In the Abelian-Higgs model, you have this charge, which you can interpret as a degree and so on. If you like, it's a degree in a line bundle. So here you have, so this is how it is generalized. So the relevant topological charge is in an element of this group. Okay. For example, when X is P1, this is going to be 2 copies of Z. We're going to see exactly what is the interpretation of that. And this is so the functional, whose critical points are going to define the fields in the model. So it's Yang-Mills-Higgs functional. I think everyone is familiar with these. So this is really a generalization. So if you look at the Abelian-Higgs model, where you also have the Yang-Mills-Higgs functional, and you interpret the various terms geometrically, you will understand that this generalizes to the situation, and you interpret the Higgs potential in terms of this moment map in symplectic geometry, and then again there is what people call the Bogomolny trick, okay, which consists of rearranging this integrand as something which just depends on the topology. So it's a pairing between this equivariant two homology class and an invariant, a gene variant two cohomology class, which comes from the moment map. So this is something that is not going to change when you change the fields continuously. And then here you have, again, an integral of some integrand, which is non-negative, and it's going to be zero exactly when these two things are zero. Okay, so this is just very similar to what I think you're familiar with from the ability model. And then you get the vortex equations. So the vortex equations consist of, I can look at this potential and say that when this is zero, then I'm actually at the minimum of this functional. Okay, so an observation. So you can also do the similar completion, but now instead of an equation like that, which says that this phi, which I call the Higgs field, is holomorphic, which is what how this equation is to be interpreted. So so I'm using the covariant derivative, and this is there's a covariant derivative on this principal on this fiber bundle, which also splits as in two parts. Okay, and this equation says that this section phi is holomorphic. There's going to be another equation so another Bogomolny trick, or if you like, an anti-Bogomolny trick, where instead of holomorphic you have anti-holomorphic, and then you might say, well, these are the anti-vortex equations. Okay, but one thing which is a bit disappointing is that in the Abelian-Higgs model, anti-vortices and vortices, they do not coexist. Okay, so either the section is holomorphic or the section is anti-holomorphic. You cannot glue together on the surface, a section which is, here holomorphic and here anti-holomorphic. Okay, but I'm going to tell you how in this more sophisticated model with a nonlinear target, then there's a way in which you can think about particles and antiparticles, which I think is quite nice. Okay, so yeah, and these are the moduli spaces. So I fix a topological class, and I say, well, I'm looking for solutions of the vortex equations, within that topological class. But I'm going to divide by the action of gauge transformations, which leave these equations. So the gauge transformations leave these equations invariant. Okay. So, any questions? So this is the space where there is the metric that I'm interested in. Okay. So now the L2 metric on vortex moduli spaces. Okay. So this is how I think of this metric, so how you can define the metric. So this is something that is most economically explained for people that are familiar with symplectic geometry and symplectic reduction. Because, what happens, so first of all, I have here a model for the tangent space, to the space of, A is the space of connections in P, and this gamma is the space of sections of the bundle with fiber, so the target X. Okay, and so this is standard gauge theory. So these spaces are these concrete spaces that are based on on the Riemann surface. These are good models for the tangent space of the space of fields at any field A phi, a pair A phi. Okay. And then there is a natural complex structure which is got from combining the complex structures on sigma and on X, and this is the metric that I'm talking about. So this infinite dimensional space of pairs A phi, it carries this infinite dimension. So this metric, which is a metric in an infinite dimensional manifold, if you like. Okay. So again, this is the case that you all are familiar with, which is the Abelian-Higgs model. Okay, so it's X C equals C with the usual, action of rotating around the origin. This is the moment map. So the moment map is, so this is the generator of, the rotations around the origin, which has some tau here because it can be specified. So it's specified just up to an additive constant. Okay. And yes, so this is what I said, that in this case, the degree of these line bundles is going to be the topological charge. And then, yeah, so if you're working on a compact surface, then so you can see that when you integrate this second vortex equation, this V2, okay. So in the first term, you're going to get basically the degree of the bundle, right? Integrating the connection. And here you're going to have two terms. One is going to be the square of the norm squared of phi. So the integral of norm squared of phi, it's the L2 norm of phi, which is a positive quantity, and then you have tau times the volume of the surface. So there's going to be so there is this thing that you can convince yourself easily that. So the second equation has only solutions if so tau times the volume is at least this large when you fix the degree of the bundle. Okay, so you get that just by integrating the second vortex equation over sigma, and then just observing that the integral of the squared norm of phi has to be non-negative. Okay, so this is usually called the Bradlow bound. So it's a necessary condition for solutions to exist. Okay, on a compact surface. And now this is a theorem that gives you a very concrete description of the moduli space as a complex manifold. Okay, so this is so there's various people that prove this, independently, and in actually some people more than in more than one way. So so assume that now you have actually the strict inequality here. Okay, then the modular space is going to be the symmetric product of the curve of the surface. Okay, the symmetric product is just the Cartesian product, and then divided by the action of the permutation group that permutes the copies of in the Cartesian product. So this action of the permutation group is not free, but the quotient by miracle. This is one thing which is very fundamental about topology in two dimensions. The quotient is going to be smooth, and more than that, the symplectic. So the complex structure on the surface. Oops. The symplectic structure on the surface is going to induce, so the complex structure on the surface is going to induce a complex structure on this complex manifold. So this on this smooth manifold. So it's going to become, in a natural way, a complex manifold of dimension k, complex dimension k, real dimension 2k. Okay? So yes. Not subtracted, exactly. So exactly, that's true. The diagonal is where the action is not free, but there is no singularity in the quotient. Okay? So you can you can understand this by introducing coordinates in terms of elementary symmetric functions and so on. This is something very easy and local and very easy to understand. Anyway. Okay. So so this is describing the modular space as a complex manifold. This is easy, but the point is that there is going to be also this metric that is going to be induced from this metric on the space of field. So the point is that you can recast this definition that I made that I've given you for the modular space in terms of a symplectic quotient. Okay, so because this space of fields has a symplectic structure, actually this space here you can regard as a symplectic quotient. So it's this equation V1 is actually going to cut out a complex submanifold of this space of fields. And then, this L2 metric that I defined here is actually a Kähler metric. Oops. It's a Kähler metric, okay? And then it turns out that its scalar form is going to induce a symplectic structure also on the quotient, because the quotient, so once you fix once you look at this submanifold that is defined by V1, okay, there's going to be an action of the gauge group, and V2 is actually the moment map for that action which is Hamiltonian. Okay, so the action of the gauge group on the manifold given by V1 is Hamiltonian. V2 is the moment map for that action, And then you can see that this is just saying that I'm looking at the zero of the moment map. So this is the moment map for the gauge action. So it's just the zero of the moment map divided by the group that the group that is actually acting symplectically. So this is really a symplectic quotient, and then you have a symplectic structure, and it's actually a killer structure on this moduli space. Okay. So again, yeah. So in the end, this is the main information, that there is a natural, from this minimal kit that I introduced, this space is going to acquire a killer structure. So both a symplectic structure and a complex structure, and they are compatible. So there's also a metric, killer metric. But yeah, as I said, the complex structure is easy to understand. Either the metric or the symplectic structure, they are hard. Okay, this is really where all the work has to be put in. Yeah. Okay. So that's what I say here. Yeah. So you have to understand the killer structure. You have to understand. So out of these three geometric objects, you have to understand two of them. Any two of them will determine the other. But one of them is easy. So you still have to either understand the symplectic structure or the killer metric. Yes. Yes, exactly. That's a very good question, coming at a very good time. Okay, so yeah, so this is, yes, exactly. So this is how how you should think of it. So I'm describing, if you like, yeah. So everything now is happening on sigma, right? But and for this Yang-Mills-Higgs functional, which you can regard as some kind of potential energy. But I can also describe a Yang-Mills-Higgs functional on, some time interval cross sigma, okay? And then you should think of these as, so there's going to be a dynamical system, okay? The Yang-Mills-Higgs functional is going to be a function in the sense of, for mechanics, right? For a field theory, a classical field theory. And then this energy that I described is the potential energy. The kinetic part of this Lagrangian is going to be basically given by this L2 metric. So this L2 metric is going to describe so if you like, so there's going to be a space of fields with some degeneracy, okay, and so this, if you like, the moduli space is going to be the moduli space of vortices is going to be the minima of the potential energy, but then there's still kinetic energy, so you can still give your field some kinetic energy. Okay, so if you kick your fields in the direction of the moduli space, they're going to move around geodesics of this metric, which is induced here, which is the metric that I'm talking about. So this is a very very useful picture that was it was introduced by Nick Manton. Okay, and this gives you a recipe to understand low energy dynamics in this type of self-dual theories. So it's you look at these moduli spaces, study their metrics, their geodesic flow is going to approximate the classical field theory in 1 + 2 dimensions. Okay. So these vortices in the Abelian-Higgs model. So my collaborator Martin Spate, he calls them usually vanilla vortices, because they are vortices which are sort of trivial. They are sort of the simplest flavor is they're just vanilla. Okay. So I know that in Italy there's also something called vanilla vortices that you can actually eat. So they are they have this shape. Okay. But let me just show you the picture. This picture of vanilla vortices scattering. So now this is how I think of this. So this picture is a picture, so there's a bit of surface, and this picture is just a graph of the energy density. Okay, so this potential energy is the integral of a sigma of some quantity, which is an energy density. Okay, and it's peaked at these 2 points, which are going to be the zeros of the Higgs field. Okay. So this is a picture, if you like, of a point in moduli space. Okay. So in this picture here, where this is the modular space, there's this isomorphism between, so for the modular space that I described in terms of solutions, modulo gauge invariance. So there is, so in this case of vanilla vortices, this map is actually quite easy to understand because it's just the, the equivalence class of A phi. Okay, so here I take just the, the divisor of zeros of phi. Okay, so phi will have some zeros. So they're going to be discrete points. So the discrete set of points on the surface, finite number of points. You have to count them with algebraic multiplicity. Okay, and there's going to be k of them. Okay, so this map for a solution will give you just a configuration of zeros, right? Maybe some zeros are going to be on top of each other. They have to be thought of as fat zeros, okay? And they're k in number. K is this topological charge, okay? So here, these zeros will be roughly at the maxima of the energy density. And now I'm going to give them some kick. I'm going to make them collide frontally. So this is what is going to happen. Okay, so they're going to scatter at 90-degree angles. Okay, so this is really what happens. So if you follow the geodesic, this is really what is going to happen. So you see that the superposition here is sort of non-linear. So you don't get just like a bump of energy energy density, and in this situation where they are on top of each other. So the energy density is circular around these points. Okay, and as I said, yeah. So this is basically how you should think about this object. So you have this space of configurations, if you like, okay? But there is more structure to that, okay? They sort of see each other and they interact somehow, as this picture shows. And this is modeled by this metric, okay? So this is a geodesic. This is a geodesic for this metric in this space. But it's a non-trivial, if you look at the field, you see that there's some non-trivial dance of zeros happening on the surface, okay? Okay, so well, this is all classical, yeah. But yeah, so I think the answer is no. But there is a way in which we can approximate do quantum mechanics on the modular space. So yes. Classical cross section, yes, sure, yeah, yeah. Exactly. So that's So this is more natural on the plane, yes, to do that on the plane, yes. And there is some studies of these cross sections, yes. So yeah, interacting. So they all have the same potential energy, okay. But still, in this minimum of the potential, there is some dynamics going on. In this sense, they are interacting. Yes, exactly. Well, the metric is defined at each position of the position of the vortices is a picture like that, right? And this defines a point on which there is an inner product, the metric there, right? And then this metric will have geodesics, and this is what I'm talking about. And as you see, the geodesics will encapsulate some kind of interaction between among these particles that, as you see, are particles on the surface, but with structure. They have some structure, and they see each other. Okay. So now I am a bit, okay, so this is, yes, okay. So now, this was the story for vanilla vortices, so just zeros, and then the zeros can be on top of each other, and I told you how they scattered. So by the way, these pictures were generated using integrability, because these equations, these vortex equations, they are integrable if you put them on the hyperbolic plane with a certain curvature. And I use these to generate solutions analytically and then plot these, make these plots. Okay, so here I am going to this, I'm going to generalize these vanilla vortices to, vortices of many different flavors. So now I can do, but it's not more involved than these. I'm just saying that I'm going to put to substitute the target, the target C, which was the case for vanilla vortices, with some toric manifolds, for example P1 or P2, or a Hilsebrook surface, or whatever P1 cross P1, whatever I please, okay? And then just like a toric manifold can be given by very simple set of combinatorial data. This is also very attractive because you're not going to get a much more complicated toolkit. Okay, you just have to give the data of so a more complicated toric manifold. So basically, what I'm saying here is that there's going to be a family of more complicated models where you just replace the target by a toric manifold. So you're still going to have a billion gauge theory. So it's still a billion gauge theories, okay? But now you're going to have a target. So targets which are going to give you actually more particles. This is really the thing that changes. I'm going to illustrate this. So there is this statement here. I'm not going to explain really what is in here, but this is the general statement for general toric targets. But I'm going to just give you a more visual picture. What happens for the case where the target is P1? So it's as follows. So just like the zeros in the abelian-Higgs model are gauge invariant. Okay, so when you rotate, the zeros don't move, right? In this case, because the rotation, so this rotation sphere also preserves this is zero. This is infinity, if you like. Okay. So also the poles. So if you think of this phi as a locally meromorphic map, okay, the poles are also going to be gauge invariant, and this is really the picture. So if you specialize this for the case of P1, this is basically the statement. Okay, that so when you have target P1, then you have basically two effective divisors on the surface. There's a divisor of zeros. So the point on the surface where phi is going to have a zero, okay? The points where phi is going to have a pole, and now zeros can come together, poles can come together, but a zero cannot come together with a pole, right? Because the phi cannot take value 0 and infinity at the same point on the surface, right? So this is how you should think of this. So there's going to be a copy of the symmetric product k plus times, which k plus is the number of zeros, and then with the symmetric product k minus times, k minus is the number of poles, but then you have to take out this diagonal, okay? So before, when you started with a compact surface, you still had a compact moduli space, but here it's not the case, because you are taking out, so this product is compact, if sigma is compact, but this diagonal is a boundary for the moduli space. Okay. So when I say that I'm interested in the asymptotic geometry of these metrics, this is mainly what I mean. I want to understand global properties, for example, like the volume. So is the volume of this metric finite, for example? And but also I'm interested in the asymptotic behavior, so describing the metric close to this boundary. So this is going to be important. Okay, so any questions? No. Okay. So this is the case where, for example, you have these vortices alla nocciole. So with another flavor, and then you see that it has two colors. You see. Okay. So here I'm going to fix the target to be a sphere of unit radius. Okay. And the moment map is that. It's just, so the moment map for the action of the two sphere, so the action of the circle on the two spheres, is just the height function. Okay, so it's just the height. Okay? And then there's also, again, an ambiguity, because you can add a constant, so this tau. So if you like, there's going to be a one parameter family of possible Higgs potentials that I can work with in this model, okay? And and then when you integrate the second vortex equation, now you have two inequalities. So this is something that needs to be satisfied for vortex solutions to exist, okay? So k plus k minus together, they give you this equivalent homology class, okay? And they tell you basically how many zeros and how many poles there are in a solution, okay? And again, you have an energy bound which has this form here, okay? and you can deduce the degree of the circle bundle associated to, by just taking the difference between K plus and K minus. Okay. So the simplest example, so basically, these vanilla vortices people have studied over time, and simplest example, so this is new, this is, so this is the case where you have a vortex and an antivortex. So I can think of the zero and the pole as somehow a vortex and an antivortex, because if you look at the flux is going to have opposite directions on zeros and poles. Okay, so in this sense, I'm having here BPS configurations, but with sort of two signs of flux. Okay, so the simplest example where there's something new happening is when you have one zero and one pole, and you really want to understand what happens when they come together. Okay, so this is, for example, what is the asymptotic behavior of the metric when in this situation? So it's when they go to the boundary. Yeah. Okay, so here, I think here I'm going to flash these a bit quick. So this is how we understand we can get our hands on these metrics. Okay, so this is okay. So there is a PDE that governs this vortex equation. So it's the vortex equations as I have presented them. They are so there is this gauge symmetry, but you can somehow you can look at this equation, the first vortex equation, okay, and solve for the gauge field, and then substitute that in the second equation, and then you get an equation like that. Okay, so for the gauge invariant quantity log mod phi squared. Okay, so this is invariant under this U1 action. Okay, and then this equation results from so substituting the solution A is as a function of phi in the second equation. It gives you this equation here. So this is very familiar, very so it's like so people that are interested in integrable systems, they will see that, well, this is like some tan H Gordon, kind of, not sin H Gordon, but, in this case, tan H Gordon. This is the equation that we are dealing with, okay? So I don't know any way in which is integrable. So, integrability, people have their own definitions and so on for integrability, but I don't know any sense in which, maybe even in a limit, this equation becomes integrable. It would be very nice to have this kind of property, but I don't know. Sorry? This is two dimensions. This is an equation on a surface. It's an elliptic equation on the surface. This is the Laplacian. So yeah. Anyway, so here, so this is the. So here I have to be more precise. I am going to the simplest example of surface, which is actually the Euclidean plane. No, X and Y. X and Y. I'm looking for static solutions, minimum of the potential, and they're going to move with this metric. Yeah? Which I want to understand. I want to understand the metric, but this is for each point on the modular space. I have some configuration of zeros, yeah, and I want to generate solutions out of this data, the position of the zeros, which appear as here as support of these delta functions. So anyway, so here, well, so let me be more precise. So we are dealing with the vortices with target P1. Okay, there's going to be these ZRs plus are position of zeros. These are positions of poles. So you have this forcing term, this delta function on the this homogeneous. There's this inhomogeneous equation, elliptic equation, and when you solve for H, this equation for H, where given these divisors, then you have generated a vortex modulo gauge transformations. So this is really what you want. It's no. Then you have just the equation of geodesics for this metric. This is something different. Yeah. Okay, so here the point is that the metric is defined in terms of fields by, the definition I gave you is a metric is defined in terms of the fields. And this is the equation that gives you the fields in terms of these, the zeros that are, a good, it's a good way of looking at solutions. It's as, points in this space of devices. Okay? And now the point, now the task, which is not very easy, is how can we extract the metric, the L2 metric from this PDE? Okay, so this is what I'm going to flash you. So this is explained in our paper. So I think if you are interested, you go to, you download our paper from the archive, and this is explained in all the details. So this is the simple situation where you have 1 0 and 1 pole. Okay, so you have to solve this equation. So I am working here on R2, which is the simplest example. Okay, and I'm making, the obvious thing to say is that, well, there is rotation symmetry, because now the isometries of the plane will relate solutions to solutions. So really, you just need to solve the equation in a situation where the distance between the zero and the pole is a fixed number. From, if you can solve this problem, you have obtained all the solutions, because you can just use the Euclidean group. Yeah. So that's basically it. So you have, you are basically, you have. So I am here. I'm saying that you have a zero and a pole at distance 2 epsilon. Like symmetrically, let's say on the real axis. Okay, and then So as you see, so the a zero at epsilon and a pole at minus epsilon, and then and then this is how So there's a way of regularizing the equation, making these. So you subtract and add something to make these delta functions disappear, and this is the equation that you end up with. So now this equation is regular. There are no delta functions. It's an elliptic equation which is highly nonlinear. So how can you, have to study it? Yeah. Yes. There's an exponent and there's a constant too. Yeah, there's a constant term and the exponent of h. Yeah. It's going to be Liouville for the hyperbolic metric with a certain curvature, and this is what I used to generate. Yeah, but in general, it won't be Liouville. It won't be integrable. Yeah. Well, it's just from the new type of moment map, which is this. Yeah, it's a modification. Yeah, it's the equivalent of Taub's equation, but for the target which is not C, but it's P1 with this action that we are very familiar with. But it gives you a different nonlinear term. Yes. Okay. So anyway, so now we can rescale it. So this is really the equation that we study. So this is the equation where. So now what I did was I've just rescaled the space so that the zero and the pole, they are sitting at plus and minus 1, and now this parameter epsilon is sitting here in front of the nonlinear term. Okay, and now you want to solve this with boundary condition that so this thing that is h hat, which is when I incorporate these regularization and this rescaling. Yeah. Anyway, so I need to solve this equation. So this is how. So you can maybe put it in a computer. And this is this is the so this is actually a picture of the magnetic field. So as I said, I advertised that you're dealing with particles and antiparticles in this sense. Yeah. So the fluxes are opposite, close to the zeros, the zero and the pole. Anyway. And now there is a gadget that we use. So I certainly need to get to statistical mechanics today. Yeah, right. So there's a very important tool that we use, which is called we call it Strawn-Samuels localization, which was already used for vanilla vortices, but now we had to adapt it to deal with these vortices with nonlinear target, which is the following statement that. So actually, what is remarkable is that when you are computing the L2 metric, which involves, solving for the linearized vortex equations and then integrating that quantity over the surface, when you try to do these compute the metric using this recipe, you will understand that there's actually a localization phenomenon that actually you can, using Stokes' theorem, you can actually reduce this calculation to just computing something at the zeros and the poles locally. So there's some data at the zeros and the poles that you can extract, and then you can get a local formula for the metric. Okay, I'm not sort of explaining these. I don't have time to explain this very well, but so there is some manipulation that you do with the integrand, and then roughly the main tool that you use is really Stokes' theorem, that when you are integrating, you have to integrate, an exact form, the complement of, small disks around the zeros and the poles. So here you have, zeros and poles, you do that for zeros and poles. And then this is some, these are some disks with a fixed radius, and then you'll see that, this thing will not depend on the radius. And when you shrink, you get this limit here, and you get a formula for the metric, so which is like that. Okay, so let me just maybe try to explain a bit here what this means. So it means that so if you look at the solution, and you look at this h, which is the log of mod phi squared, okay, expanding into, so in this case around a zero. Okay, you have this log term because there is a zero. So here I'm assuming that it's a simple zero. And then there's something else which is regular that you expand as a Taylor series. So it turns out that these linear coefficients is really just the only thing that you need. So these are going to be functions that depend on the positions of the zeros and the poles. Okay? Yeah? So the only dependence on the coordinate of the surface are, so here and in these, so here, right? So you are Taylor expanding in that coordinate, okay? But then only, so these linear coefficients actually are relevant. So this is for the zero, this is for the pole. There's a different sign here in front of the h. But this is really what you need for the metric. So after you use this localization, you will understand that, the metric on the modular space, in this Euclidean case, which is easier to understand, is going to be, so not just the obvious metric that would be induced from the Euclidean metric on, the Cartesian product, but there's a correction. Because that metric would not be regular, okay? So I told you that the modular spaces, even with this quotient Euclidean diagonal, they are going to be smooth manifolds, as complex manifolds, but not metrically. Metrically, there's going to be a cone there, and this correction is sort of going to regularize that cone. Okay, so this is a very nice formula for a local formula for the scalar metrics on the modular space. Okay, and now we have here, you can basically say that, well, it's, because I can factor out the translations, I'm looking at just a metric on the cylinder. And these are polar coordinates, and I'm just after this factor that depends, it's a real function depending on the separation of the zero and the pole. And yes, so and now there's some magic occurring. So we observed by looking at this numerical work, generating the solutions, that asymptotically, when h is small, when you are actually close to this boundary, there is some kind of self-similarity behavior. So this thing here is true. And then when you plug these ansatz in the vortex equation, you can solve for this profile f star. So in the end, so these are basically, so these are plots. So plots of this profile for different values of separation. And you see that when the separation is very small, it doesn't really, so they actually fit into a curve. And you can actually solve for that curve. Okay? So in the end, you get the following. You really get, for small epsilon, you get really the very precise asymptotics for this conformal factor. And you can basically say anything you want about the local geometry close to the boundary. Okay, so for example, yeah, so this is the, so there's going to be a similar statement at infinity, and this is actually, yeah, this is similar to something that people had done already for vanilla vortices, but this is the results which are new and I think actually more difficult. So yeah, so this is the asymptotic geometry, which is important for this sort of more general problem. Anyway, so this is a picture of this cylinder embedded in R3, and what turns out is that in this case the Gauss curvature is blowing up at the boundary. Okay, so there's, yeah. Anyway, so now all of this was in this simple situation where you have just the Euclidean metric on the surface. Okay, but now I'm interested in the compact. Okay, so compact surfaces. I'm not actually going to explain you today why I'm interested in compact surfaces, but this is what happens when you do exactly the same trick. So you, yeah. So now I'm working with sigma to be S2. So there is this S2 in the target, but now my sigma is also S2, and then there's this extra factor here. And well, anyway, so here, for example, we can prove in this paper, you can see that we can prove, for example, that the volume is finite. So rigorously, just by doing doing analysis with this elliptic PDE, so you can prove that the volume is finite, and we can compute the formula for the volume. And anyway, and we can also prove that the metric is incomplete, that you can actually reach the boundary by a geodesic in finite time. Okay, so this is just analysis, using estimates, Sobolev spaces. Yeah, anyway, so we can prove these results rigorously. But now let me get to the statistical mechanics. Okay, so now this is the situation that I'm going to describe. Suppose that your surface is a compact surface with some fixed area. Okay. So this is the first type of result, which I am not going to explain in detail. You look at the paper. So there is a way in which we can compute not in the sense of rigorously as in these theorems that I was flashing before, for the sphere, but we can. There is using some very reasonable conjectures, we can deduce. So we can basically approximate these gauged sigma models with the target P1 by a gauged linear sigma model with target C2 by lifting the quotient P1 as a quotient of C2 minus the origin by C star, right? We lift it in that sense to C2. And then we deduce, so the advantage is that in the gauged linear sigma model, the moduli places are compact. And then you can compute the Kähler class for these metrics. And then if you know enough about the cohomology ring of symmetric products, you can compute the volume. No, not really, no. So we are looking at vortex equations on this sort of lift. So in this sense, there is some ellipticity involved, but yeah. So we are approximating. So I think this is a fair way to say. We are approximating these vortex equations that I'm describing, for the nonlinear target, by the vortex equations in this linear model. And but there's more symmetry in the target, and what we do is, so it's basically, this picture. So we are sort of shrinking. So this lift will have a symmetry T2, so a torus, and we are shrinking one of the directions. Okay, and the other direction is the U1 that is acting here. So in a way, this is explained in the paper anyway. So there's actually there's this way of sort of doing this. So there's a one parameter family of gauged linear sigma models, and then in the limit we argue that we expect that because the equations are going to be the same, that the solutions will also converge. Okay, and then more than that, you might think that, well, if you can compute then the volume, for this family of gauge models, it's a one-parameter family of volumes. The limit will be the volume of this moduli space that I'm interested in. So in the end, we have really a formula for the volumes, which we say in the paper it's sort of heuristic, because the details of these analyses, I mean, this is quite difficult to implement, but I mean, I bet that these formulas are really correct. And in fact, they coincide, if you specialize to the two-sphere case, which is the case where we studied rigorously, you recover the same form that we obtained. Okay? So now so this is the result. So this is the result so now this is actually independent of the genus. So for any surface of any genus, you have, V is the area of the surface, and this is the volume of the modular space. So for all tau, the tau, so the tau is here, the tau, so I'm actually working with arbitrary, sort of Higgs potential, So now statistical mechanics. Okay, so I am going to study now. So just as I said that, I can, we had this picture, this very nice picture of the modular space, which is a space of, fields with minimal potential energy, okay, with this metric, and the geodesic flow is approximating the classical dynamics at low energy. Then you can do also statistical mechanics in this sense, okay? So you have a class, Hamilton's equations, so canonical equations in this space. So this is the phase space, canonical symplectic form, okay? You have this Hamiltonian, which is basically the Hamiltonian for geodesic motion. The potential energy, as you see here, is constant, but there's still some interesting dynamics, okay? And then we are interested in this thermodynamical limit, where you have the number of zeros is going to become large, the number of poles also, okay? And the volume, or the area of the surface is also going to become large, but in such a way that the density is finite. This is the natural thermodynamical limit, okay? So yeah, and this is what you can do. So you can integrate out along the fibers as just Gaussian integration, okay? And then in the end, you have a partition function which is just proportional to the volume of the modular space. So this is really the part of the partition function which is non-trivial, okay? And anyway, so here is the free energy, okay? And then in the asymptotic, in this thermodynamical limit, you can simplify this using these asymptotics. Just discard what is happening here, using Stirling approximation, which is more than allowed. It's actually needed in statistical mechanics, right? We get to very we can do this we can do this exactly. So we can compute entropy, okay, and the pressure. So if you like, this is going to be like an equation of state for these vortex gases. So now if you take these, so in all these quantities, for example, the entropy or the pressure, there's going to be this quotient G over V. G is the genus of the surface. So if you say that, well, you are working at fixed genus, and then in the thermodynamical limit you take that to 0, okay, then you end up with what is, I think we should regard as the workable pressure and the workable entropy for thermodynamics of these systems, and they are going to be, yes, genus independent. So this is I think this is something that we can show that. So you put the gas on throw some large number of vortices and antivortices on a large surface. Whatever they do together, this is independent of the topology. So this is a sort of result, and is actually also the same for vanilla vortices. So these calculations that we do, this is inspired by work by Nick Menton for vanilla vortices, and again, this independence of the genus we recover. What is new is that yes, we now have two two species of particles. So we are dealing with actually not just a gas of particles, but a mixture of gases. In this case, you have two types of particles, okay? And then we have, for example, virial expansion. As advertised, this is all exact. So we have a virial expansion, all the coefficients to any order, we can tell you what they are, you know. And there are coefficients for the zeros, for the anti-zeros, and mixed coefficients. Okay. And now we can do something which does not make sense for just one species, which is studying the entropy of mixing. Okay. So now suppose that you do this thought experiment. You divide the surface in two surfaces, sigma plus and sigma minus. You put all the zeros on one side, all the poles on the other side, in such a way that the area, the total area is the same, right? And there's the same pressure on both sides. So compare the entropy of the segregated gases with the mixture, right? And the difference is the entropy of mixing, and we can compute it. And it's very much so. So this is the result, and we can show that it's positive, as you might. This is sort of the natural thing to expect, I guess, right? And it's a non-trivial perturbation of the classical result by Gibbs. So when you have ideal gases, this is one of the things that people that you have explained your undergrads. How to compute the entropy of mixing for a mixture of two ideal gases, right? So the result is going to be exactly that without these coefficients. So without this extra term. So if you replace this here by 1, you get the classical Gibbs entropy of mixing. But here we have, we are dealing with this, I think, non-trivial system of, so we are modeling the interactions by, geometrically using this metric, as I said, and still we can do this calculation exactly. So I think it would be nice to maybe, understand. So as I said, it would be nice to use these kind of explicit results to say something about the interactions, which is what I'm also interested in. So effectively, this is giving you a picture of how these, zeros and poles interact. Can you say, more about the sort of how the individual particles maybe interact locally? I don't know. I think so. Clearly, this is going to be contained in all of this. So how to extract this information? I think this is going to be hard. Okay. Yes, I finish here.